Up until now, most of our acids that we've talked about are called monoprotic acids. That means they only have one ionizable hydrogen atom. So there's one hydrogen atom that can be donated to the solution. We can also have what are called diprotic acids or even polyprotic acids. That would be two ionizable hydrogen atoms or more. Something like phosphoric acid is a polyprotic acid. It contains 3 ionizable hydrogen atoms. Now, when we have more than one ionizable hydrogen atom, we have more than one Ka value. The first Ka is always going to be greater than any subsequent Ka values for that molecule. For example, in sulfuric acid, the first hydrogen to come off, hydrogen. So the first Ka value is much greater than 1. The second ionization, however, is a weak acid ionization with its Ka value, A value. These polyprotic acids will undergo a stepwise ionization, and that occurs for all of our polyprotics. So when we start with our K value, we'll start with the first proton to come off, and then the second proton to come off will start with an initial value of the conjugate base. So here, the conjugate base of carbonic acid is this bicarbonate anion. So then that bicarbonate anion becomes a reactant in the second ionization because it is the acid that a hydrogen is going to come off of. Now, because the first ionization is always a stronger ionization with the Ka value much greater than the second Ka, the concentration of the hydronium ion is almost always dependent on the first ionization rather than the second. So let's do a calculation. When we buy soda water or carbonated water, then we have carbonic acid in our water. So we have these 2 steps for a diprotic acid, and the question asks us to calculate the concentrations of the various ions in the water. So let's start with our carbonic acid, and I'm just going to dissociate this into proton and conjugate base. So we're going to start with 0.033 molar, and I need you to see that this way is just as good as reacting it with water. Depending on where you go from here, you might see your weak acids dissociate like this. So I need you to be prepared for different ways that instructors will show you. So we will change this by some value x. We don't know that x yet. Then we have our equilibrium values. Now I'm working with the first ionization. So I'm working with Ka1, which is 4.3 times 10 to the negative 7. That's going to be equal to the concentration of my products, which in this case will be represented by x squared, over the concentration of my reactants, 0.033 minus x. Now it looks like I can simplify this, so I'm going to go ahead and do that. And when I simplify it, I get x squared over 0.033. When I work that arithmetic, I get an x value is equal to 1.2 times 10 to the negative 4. Now that's currently going to be equal to my concentration of my hydrogen ion or hydronium, as well as my conjugate base. Now this conjugate base becomes an acid in the next reaction. So I'm going to change colors here so that we can try to keep track. So in my second reaction, when I have the second hydrogen that's going to come off, I'm going to start with an initial concentration of HCO3, the bicarbonate anion, of 1.2 times 10 to the negative 4, because that's what I just calculated. Now I also have 1.2 times 10 to the negative 4 of my hydrogen ion, but I have no carbonate anion yet. So my change is still going to remove from my reactants and add to my products. Then at equilibrium, I should have something that looks like this. And I'm using the second Ka. So I'm Ka2 is 4.7 times 10 to the negative 11. And then that's going to be equal to my equilibrium concentrations. And because my initial concentration here is more than 1,000 times different than my Ka, I am reasonably sure I can simplify this. And when I simplify this, then these factors cancel out, and my X value is equal to 4.7 times 10 to the negative 11. That's a capital M molarity. So my equilibrium concentrations then are going to be the concentration of my carbonate anion is going to be equal to this X value, 4.7 times 10 to the negative 11, capital M molar. The concentration of my hydrogen ion is going to be 1.2 times 10 to the negative 4 plus my X value, 4.7 times 10 to the negative 11, which is fundamentally 1.2 times 10 to the negative 4, capital M molarity. The concentration of my bicarbonate, HCO3 minus, is going to be 1.2 times 10 to the negative 4 minus this X value, 4.7 times 10 to the negative 11, which is also effectively 1.2 times 10 to the negative 4th. So although the concentrations of my hydronium ion and my first anion are heavily dependent on K1, the second anion is solely going to be dependent on K2. Now we can have polyprotic acids and polyprotic bases. Now when you say a polyprotic base, what that means is you have a base that can accept more than one proton. So a diprotic base, an example of that is the carbonate anion. Let's see if I can highlight it right here. That can accept 2 hydrogen atoms. So that means this is a diprotic base. It can accept 2 protons.